Hey everybody, welcome to Unit 3. The topic of Unit 3 is bonding, VSEPR, and hybridization. I'm going to start you out with this little joke. Take a look at the kid writing HIJKLMNO, saying, "I thought you said the chemical composition of water was H2O. Ha 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 ha." All joking aside, let's talk about bonding. This first video lesson is going to cover the basics about bonding and a little bit of review of what you learned about in chemistry and honors chemistry last year. In a chemist's mind, there's no simple yet complete way to define what a chemical bond really is. We like to define them as ionic or covalent or intermolecular forces that may be attracting molecules to other molecules. But in a chemist's concept of bonding, there is no one way to define chemical bonds. And rather, we talk very broadly. We say they are just simply forces that hold groups of atoms together to make them function as a unit. A bond will form only between atoms in order to achieve a low energy state. Everything wants to be as stable as possible. And in order to achieve that, bonding may occur. Now, sometimes two atoms might not want to bond. Sometimes their most stable state is not bonded. Like in an example, maybe where two noble gases come in close contact with one another. They are more likely to stay separated rather than bond together. They're not going to be attracted to one another. Their lowest energy state is separate. But whatever that low energy state is different between two atoms. And I'm going to show you an example on the next page using hydrogen and an energy diagram in order to illustrate. Stable bonded compounds have less energy than if their atoms were floating about alone. So again, stability drives bonding. Take a look at two hydrogen atoms over here on the right hand side of this graph. We often like to read graphs from left to right, but I'm going to start reading this graph from right to left. You've got two atoms of hydrogen, and this line represents the relative energy of these two atoms as they are in relationship to one another. Now, separated from one another, they're actually pretty unstable. This red line is pretty high, up close to zero, and you're thinking, well, zero is nothing. Well, actually, zero is something. Zero is pretty high in this case. Remember, in terms of stability or energy, the lower the energy, the more stable. And if you can get negative energy, that's even better than zero energy. Positive energy, way unstable. But in this case, the two hydrogens are close enough to each other, but far enough away from each other to represent an energy state that is close to zero. Now, as you see, what we're doing as we move to the left is we are decreasing the internuclear distance between these two hydrogens. And as they get closer to each other, the line begins to drop, meaning they're becoming more stable. And they're becoming more stable, and they're becoming more stable. Now we reach this point right about here, where the hydrogen atoms are pretty close to one another, and they're starting to achieve a more stable state. Now if we get them and push them closer together and closer together and closer together, eventually they reach the point where they're close, so close or close enough where they have achieved the most stable state, and their energy is as low as it's going to go, negative 458 kilojoules per mole, in fact. That's how much energy is released when these two atoms come in close contact with one another. Now, as you continue to move to the left, you'll notice that the pink line begins to turn up. And how is that possible? Well, you're smashing these two hydrogens too uncomfortably close together. And their nuclei are too close, and they begin to repel one another. And the repulsive forces cause them to become unstable. And eventually, you get a point where it goes off the chart in the positive direction. It's so positive that means that they're so unstable that they do not want to be close together. So there's an issue of being too close together, and there's an issue of being too far apart. And it's kind of the Goldilocks. Not too hot, not too cold, but just the right distance apart. And we know that a bond forms only when it's at its most stable or lowest energy state. And then I go ahead and throw a slide down that looks like this. After just telling you that there's no real ideal way of explaining bonding, will we actually go ahead and default back to the two terms that you're more comfortable identifying bonding as ionic or covalent. So yes, it's unclear about how bonding is actually defined. We, as chemists, like to define it in very general terms. But then we actually go back to these terms because it does in a way, help us understand how the atoms are interacting with one another a little bit more clearly. And so we do end up identifying ionic and covalent bonding. And maybe at first you thought, oh, great, AP chemistry, we're just going to get rid of the concept of bonding. Well, that's not really the case. Ionic bonds and covalent bonds are still a thing, and also metallic bonds, but we'll get to that. So in our concepts of bonding, once again, ionic bonds are when electrons are transferred. Typically, this happens between metals and nonmetals, where the metal has an extra electron and a nonmetal is needing an electron to fill its outermost energy level. As long as it has a full outside energy level, it is happy and stable. And so metals and nonmetals will transfer electrons. Metals will transfer electrons to nonmetals. The resulting ions will then have an opposite attraction to one another, and that attraction results in an ionic bond. Covalent bonding, on the other hand, are when electrons are shared equally between each other. Now, I should preface this by saying that only a pure covalent bond is where electrons are shared equally. That is a situation where we have like diatomic molecules, well, H bonded to H, or Cl bonded to Cl, or F bonded to F. Only in those pure covalent bonding situations are electrons shared equally, because most covalent bonds, the electrons are shared unequally. And that's what we're going to talk about there at the bottom. But before we get there, metallic bonding. What is metallic bonding? Well, we'll actually talk about this at greater depth at a chapter later on. But metallic bonding is basically this concept that you have all of the nuclei of the metals kind of just existing in this grid shape, where you've got vertical columns and horizontal rows of metallic nuclei. And the electrons that belong to those nuclei kind of exist in what is known as a sea of electrons, where all the nuclei are sharing the electrons, and that results in some interesting characteristics of metals, such as their ability to conduct electricity, their ability to conduct heat, their ability to be pounded very thin, malleable. And so these are evidence that metallic bonding exists. We'll talk more about metallic bonding at a later chapter. But let's talk about these intermediate cases of covalent bonding. Intermediate cases of covalent bonding result when there's an unequal sharing of electrons, where one atom has more pull on the electrons compared to the other atom, and as a result, the electrons are not shared evenly. Well, when that happens, we need to identify which element is pulling on the electrons more with this symbol known as the dipole. Now, a partial positive, and that's what this little squiggly line represents, is a partial positive and a partial negative. It's not a full positive or a full negative, because one atom isn't removing the electrons from the other. If it did, it would be an ionic bond. And if it did remove an electron, it would be fully negative charge. And if it did lose an electron, it would be fully positive charge. But this is a situation where the atoms are not sharing equally. So one side of the bond favors more electrons, and that would be the partial negative side. And the other side of the bond has less electrons, and that's partial positive side. And that unequal sharing, as I mentioned before, is called a polar covalent bond. Now, how do you know if an atom is pulling equally or unequally on the electrons compared to the element that it's bonded to? Well, we use the concept of electronegativity to determine which element is pulling more strongly on the electrons. The trend for electronegativity is that it increases across a period going to the right, and also increases going up a group. So the most electronegative elements are in the upper right-hand corner of the periodic table, excluding the noble gases. And the least electronegative elements are in the lower left-hand corner of the periodic table. This means that the most electronegative element is fluorine, and it has an electronegativity of 4.0, and the least electronegative are cesium and francium in the lower left-hand corner. It's important to note that electronegativities don't have a value. They're a unitless value. They are just a number that judges strength of pull on the electrons when in a bond. Here's a cool periodic table of electronegativity values, and as you can see, the columns increase in size moving to the right across the period, as we talked about. The trend is electronegativities increase across the period to the right, and they also increase going up a group. And so you can see this very clearly. The lowest ones are in the bottom of the group, and the tallest columns are in the upper parts of the group. If you ever have to judge the bond polarity, you'll be given the electronegativity values of the elements in question, or you'll be given a small table of electronegativity values in order to judge the polarity of a bond. And the polarity of a bond, once again, is how strongly one element is pulling on the electrons in a bond compared to the other element making up that bond. Here's some quick questions to check your concepts of electronegativity. First one, if lithium and fluorine react, which one has more attraction for the electron and why? Well, obviously, the answer to that one is the fluorine. We talked about how fluorine has the largest electronegativity of any element on the periodic table. So whenever it's in a bond, fluorine is doing the most pulling on the electrons. Now this next one is once again an easy one, but fluorine once again wins. In a bond between fluorine and iodine, which has more attraction for the electron? Once again, fluorine has the most. It has the most electronegativity, and no matter what it's bonded with. Now iodine is another halogen, but it's further down the column. Iodine has a fairly strong electronegativity compared to other elements, but fluorine will always beat out iodine. Here's a good little graphic that it's useful to take a look at. But it basically talks about the relationship between electronegativity and bond type. Now as you look at the top of this column, if the electronegativity difference, meaning take two elements and subtract their electronegativities, if their difference is 0, then that represents a pure covalent bond. That means that all the electrons are being shared equally. Once again, that situation is when you have like a diatomic molecule. Now as the difference in electronegativity between the two elements gets larger, the two elements are sharing the electrons less and less. And in that intermediate range is when you hit a polar covalent. So pure covalent has 0 difference in electronegativity. As the electronegativity difference increases, you get more polar. And eventually, that difference in electronegativity becomes so large that the bond type flips to ionic. And so ionic is just a really, really strong polar covalent, if you want to think about it like that. Another way to think about ionic and covalent is that if the covalent characteristics of a bond are high, then its ionic characteristics are low. The more covalent it is, the less ionic it is. They're like inverse of one another. But the more ionic a bond becomes, the less covalent it becomes. So think covalent is pure sharing, ionic is not sharing whatsoever, and those are inverse of one another. Now you might remember a little picture from last year that said that if you take the difference in electronegativities between two elements and they fall between a certain range, then you can identify it as covalent, polar covalent, or ionic. Well, let's recreate that. You've got a line, and starting at 0 over here on the left, that's a pure covalent. And anywhere between 0 and 0.5 is considered pure covalent. Now, as the difference falls between 0.5 and 2.1, we call that polar covalent. But just keep in mind that if the difference is really close to the 2.1 line, it's way more polar covalent or way more unequal sharing of electrons. And so it's approaching ionic. And if it falls right on the 2.1 line, it might be ionic, it might be covalent. It kind of depends. But as you approach that line, it becomes less covalent and more ionic. Now, we say on the other side of the 2.1 line is when it becomes fully ionic. Let's do another reality check, and this one will be more difficult than the last one, I promise you that. It says arrange the following bonds in order from most to least polar. Now let's take a look at set A. Now we know fluorine is the most electronegative, and as you get further to the left, it gets less and less electronegative. So if I look at these three molecules and I figure out which of them is the most polar, well basically I'm trying to figure out which two elements are furthest away from each other. Which element, either nitrogen, oxygen, or carbon, is farthest from fluorine. The further away is from fluorine, the more polar it is. And carbon's the furthest away, so that's the most polar. Then the next closest would be nitrogen, and then the one right next to it is oxygen. So if I ordered them from most polar to least polar, it'd be carbon, fluorine, followed by nitrogen, fluorine, and then finally oxygen, fluorine. Now I can think of the same kind of concepts. The further the two elements are away from one another, the more polar they become, if you're thinking about it in terms of electronegativity. Well, once again, one that's bonded to fluorine is going to have a pretty polar situation. In set B here, fluorine and silicon are fairly far away from one another. Carbon is above silicon, so carbon and silicon are about the same distance away from fluorine, but since carbon's above it, it's actually slightly higher electronegativity, I should say, than silicon. So the most polar, once again, is this furthest one on the right, fluorine bonded to silicon, followed by fluorine bonded to carbon. And then oxygen and nitrogen are right next to each other, so those are the least polar of these set B. Finally, we've got a set C, where things are all bonded to chlorine. Now, the first one that jumps out to me is Cl bonded to Cl. That one's definitely not going to be polar. That's the least polar. That has electronegativity difference of 0. So I can identify that one as the least polar of this set. Now the next two that I have to decide is which of the two, boron or sulfur, is further from chlorine. Well, boron is way further from chlorine than sulfur is. In fact, sulfur, I think, is right next to chlorine. And so boron and chlorine is the most polar, followed by sulfur and chlorine. And then finally, once again, we identified this one as having essentially 0 polarity. The last thing we're going to talk about in this video is the difference between bond dipoles and molecular dipoles. A molecular dipole, or sometimes referred to as a dipole moment, is when you take into account the bond dipoles and the overall shape of the molecule. And sometimes in that molecule, the bonds are not distributed evenly around that molecule. And if they're not pulling equally on both sides or all sides of that molecule, well then the molecule may carry an overall or a dipole moment. I refer to it sometimes as an overall dipole or a molecular dipole. These all mean the same thing. But bond dipoles are only identified using differences in electronegativity. But an overall dipole or a molecular dipole is factoring in the bond dipoles and the shape of the molecule. Just like in a bond, the electrons might not be distributed evenly throughout the bond, well, that might also be the case in a molecule that is made up of multiple bonds. So typically what we do is we use an arrow to represent that dipole moment of the molecule, and it's a vector. A vector is an arrow with a direction and a magnitude, and the arrow points towards the more negative portion of the molecule, and the back tail, which is usually crossed off as a plus sign, is closer to the positive area of that molecule. Sometimes that dipole falls on bonds in a molecule, but sometimes it falls into empty space between atoms in a molecule. So it really just depends. But pay close attention on these next couple of examples that I'm going to show you about where the dipole moment is being placed on the molecule. Here's a look at carbon dioxide. You have carbon in the middle and oxygens on either side of the carbon. Now, the carbon-oxygen bond on the one side of the carbon dioxide has a dipole. It has a bond dipole. It has an unequal sharing of electrons. The oxygen is more electronegative, so it is pulling on the electrons, and because of that, it has a partial negative charge. And the carbon has a partial positive. But that's happening also on the other side of the carbon dioxide molecule, where the other oxygen is a negative, and the carbon, once again, is a positive. So that's why we identify this carbon as having two partial positive charges. Now, if we identify, instead of using this notation, if we use vectors, then we represent the bond polarity using the vector pointing to the left with a cross tail at the carbon and a vector pointing to the right with a cross tail on the carbon. Now, because these vectors are in opposite directions, they cancel one another out. Now, overall, the molecule is nonpolar, but we still can show the vectors of the dipoles of the bonds. Now, this final look is basically a heat map of where the electrons are located, and the regions that are shaded orange and red, those are where electrons are more likely to be found, and the regions shaded blue or green are where the electrons are less likely to be found. And so you can see that because of the unshared electrons in the dipole of the bonds, that the oxygen is pulling on the electrons more, well then you're going to find the electrons on the oxygens more so than you're going to find them on the carbon. And because there's such a strong dipole pulling on either side, you'll see that the edges are red and the middle is blue. Now, all three of these are to look more closely at carbon dioxide and take a look at its bond dipoles. But if we were to identify the overall or its molecular dipole, we would say that it has no dipole moment. It is a nonpolar molecule because the vectors are going in opposite directions, once again canceling each other out. Here's the last molecule we're going to take a look at. And you'll notice, once again, that I have one element in the middle and two arms coming out the sides of that central atom. But this time, the oxygen is in the middle rather than the outside. So the oxygen is in the middle and the hydrogens are coming off the oxygen. And this, of course, is water. Now, oxygen is more electronegative than hydrogen, and so the electronegative element has the partial negative charge. And so the hydrogen has the partial positive charge. And so the bond dipole here between hydrogen and oxygen is pointing in towards the oxygen. Now the bond dipole on the other one is also pointing in towards the oxygen, so the resulting situation is you have two partial negative charges on oxygen and partial positives on the hydrogen. But notice how these vectors are not opposite of one another. You see, this one's pointing up and to the right, and this one's pointing down and to the right. Because both of them have a portion of their vector moving to the right, they are not going to cancel each other out. In fact, because of their direction, their magnitude is fine. They may cancel each other out, but the fact that their directions don't cancel each other out means that there's a general move to the right of the overall molecular dipole. In this middle picture, you'll see that the water has an overall dipole that is pointing towards the negative side, or the oxygen side of this molecule, where the positive is an empty space between the two hydrogen atoms. And this represents the overall or molecular dipole of this water molecule. Once again, you see the heat map of where the electrons are located, and once again, where the electrons are located are where the oranges and reds are, and the electrons are way out here on the top of the oxygen, and they're lacking electrons down here near the hydrogens. But this is an example of a molecule that has a dipole moment. It is a polar molecule because the vectors for the bonds don't cancel each other out, and as a result, you have a net dipole moment. Well, that takes care of this video lesson. Thanks for watching.